You get to see the magic happen. Hello, this is Mr. Huff, and let's take a look at what we are doing in Principles of Engineering, looking at this truss. Okay, so the key to some of this is to understand that first, we have already solved using the moments and the sum of the forces in Y, and some trig to understand what the reaction force at point A in the X direction is, what the reaction force at point A is in the Y direction. So all of these are in pounds, and the reaction force at point C in the Y direction. Also, we've calculated the angles here and here. One of the things you want to do as you proceed through this is update your diagram as you go. So we're going to start at either point A or point C because those are the places where we know the most information. So let's begin at point A in the Y direction. So we're going to assume that everything is in tension starting at point A. So I'm just going to write A, and we're going to look at the sum of the forces in Y. Then we're going to think about what that means. That means that if we add the reaction force at point A in the Y direction and the reaction force of the line from A to B in the Y direction, that's going to be equal to 0. One of the things we need to do is understand what is equivalent to the force at AB in the Y direction. So we're going to use the sine function. Remember, sine is equal to opposite over hypotenuse. And using this, we can find that the force at ABY is equal to the force on member AB times sine of the angle. Okay? So we're going to replace force ABY with F force of AB times sine theta. So let's write this down again. We can write it like this. We also need to move the force of AB and Y in the Y direction to the other side. We'll do that separately. So in 2 steps, I'm kind of spreading it out, going slow. So RAY plus FAB sine theta equals 0. So that means that RAY equals negative FAB sine theta. Good so far? So now we need to just plug in some numbers. So we want to get FAB by itself and move sine theta to the other side and move the negative to the other side. So if we do a little bit of algebra, we end up with minus RAY over sine theta equals F on member AB. And then we plug in the numbers that we have, minus 350 over sine 53.13 equals FAB. All right, and we do the calculation and we find that FAB is equal to minus 437.5 pounds. And because it's a negative number, we know that that is in compression. Okay. So we've updated our diagram. Now we're going to look at what's happening at point A in we're going to look at what's happening at point A in the X direction. So this time I'm just going to not talk you through all the steps. I'm just going to write them down and then discuss it after I finish. All right, so let's rewind and see what I did. I said that the sum of the forces in the X direction are equal to 0. So that means the force on member AD plus the force on member ABX in the X direction will be equal to 0. And that means that the force on member AD is equal to the negative value of the force on member AB in the x direction. I switched to green to show that cosine is equal to adjacent divided by hypotenuse, and if we rearrange that to solve for the force in the x direction, we get the force on member AB, which we know, times cosine of the angle is equal to that force in the x direction. So I replace with the equivalent term and then calculate it using the negative and the negative 437.5, so that ends up being a positive. We calculate that and we get that this is a positive 262. I put 6, it's actually 2. 266.2, not 266.2, 262.2 pounds, and it's in tension because it's positive. So we go update our diagram right here, saying that this is in tension 262.2, okay, on that member. And now we're going to move over to point C, and again, I will not talk as I work this out, and then we'll discuss it after I'm done. All right, so we just found that the member from C to B is negative 302.3 pounds. Let's go look at the math. So we start by taking the sum of the forces in y is equal to 0. The two forces that are interacting there are RCY, the reaction force, plus the force on member CB in the y direction. So that means that RCY is equal to the negative value of the force on member CB in the y direction. And then I switch to a different color to show that sine is equal to the opposite over the hypotenuse. And if we use that, we can write the equivalent term for the force on member CB in the y direction as the force on member CB equals sine theta. And then I replace the force in the y direction with that equivalent term, rearrange that with a little bit of algebra to solve for the force on member CB. So we have a negative 150 divided by sine of 29.74 is equal to the force on member CB, and we get that it's negative at the end, and that tells us that this member is in compression. All right, now we need to look at point C again, and this time we're going to look at the x direction. So the sum of the forces in x have to be equal to 0. Not theta, 0. Okay. Assuming everything is in tension, we're going to write this down. So the force on C to D, that bottom member going to the center, plus the force on CB in the x direction are equals 0. And that gives us the force on member CD must be equal to negative FCBX. Okay. Then, and I should be drawing some triangles along here. We'll do this in class a little bit, but okay, so we are going to switch to green, and I'm going to show you that this is equal to this. I'm going to stop talking. All right, so what we just calculated is that the tension, that the member is under tension, and it's 262.4 pounds. So we have a little bit of a difference here because of rounding errors, but you can see that these are the same tension on both sides, which kind of makes sense. If you're pulling down in the middle, it's going to have tension both ways to keep it from moving. So those two are virtually the same number. Let's go look at what we did to get there, just reviewing it. So we're looking at the point C. Sum of forces in the x direction has to be 0. We look at member CD, the force acting there, plus the force on CB in the X direction, those have to be equivalent. So that means that, that means that the force on member CD has to be equal to the negative value of the force acting on member CB in the X direction. It's good to draw pictures of triangles as you do this. I switched to green to show you that cosine is equal to the adjacent divided by the hypotenuse, and we are solving for the adjacent. So that means that the force on member CB, the hypotenuse times cosine theta, is equal to that force in the X direction. So I replace CBX with this term, and then we plug in our numbers and we get this value, and it ends up being positive because the negatives cancel out, and we know that that member is under tension. We're almost there. All right, last one is at point D. Point D, we're going to look at the sum of the forces in the y direction. That has to be equal to 0. We're going to assume everything's under tension. So F B to D equals, nope, plus the force at point D is equal to 0. And that tells us that the force on BD is equal to the negative value of FD. And there's nothing else going on here. There's no trig to do on this one because it's straight up and down. So we plug in the numbers that we know. FBD equals negative. And we know that because the force is going down, we used that previously in our summation of forces for finding the reaction force at A. We know that that is a negative 500. And when we look at this, those cancel out and we get that force BD is equal to 500 pounds. So let's go, and that's under tension because it's positive. Let's see if that makes sense. So we go up here to our diagram one more time. And we write 500 on this member, and we can see that 500 is opposite of the negative 500. So there's a lot of tension on that member. So if you were analyzing this, you would say that would be the first thing that would break. So we can see that the negative numbers are in, so the negative numbers here are, give me a second, are in compression. So we have compression, and the other three members are in tension. And if you look at it, it kind of intuitively makes sense that if you put a force on the bottom, it's going to put tension on these three members and compression on the top. So that is a completely worked example with all of the trig. I hope you find this helpful.